Welcome to SciSense, where we unwrap scientific research, because science should not be a puzzle.
Mike, I am so excited to talk about this today. Scientists just achieved something that seemed almost impossible. They made the first X-ray laser that uses mirrors and a cavity, just like a regular laser pointer.
Wait, hold on. Don't we already have X-ray lasers? I thought those giant facilities, the free electron lasers, were already a thing.
Yes! Great question. We do have X-ray free electron lasers, or XFLs, and they're amazing. But here's the thing. They don't actually work like the laser pointer in your drawer. They're more like, imagine shouting down a very long hallway once. Your voice gets amplified as it travels, but then it's done. One pass and gone.
Okay, so what makes this new one different?
This new laser uses a cavity, mirrors at both ends that bounce the X-rays back and forth, thousands of times. It's like being in a concert hall with perfect acoustics where your voice keeps bouncing around, getting stronger and more refined with each reflection. That's true lasing.
But wait, I thought X-rays go through everything. How do you even make an X-ray mirror? My dentist uses X-rays specifically because they go through my teeth.
Aha! That's the genius part. You're absolutely right. X-rays punch through most materials. But the researchers used diamond crystals, and at just the right angle, these diamonds can actually reflect X-rays. It's called Bragg reflection. The X-rays bounce off the planes of atoms inside the crystal structure.
Diamond mirrors. That sounds expensive.
Well, these aren't jewelry-grade diamonds, but yes, they need to be incredibly precise. We're talking about positioning these mirrors with accuracy thinner than a virus, about 100,000 times thinner than a human hair. If they're even slightly off, the whole thing falls apart.
Okay, so they've got these impossibly precise diamond mirrors bouncing X-rays back and forth. What's the big deal? Why is this better than what we had?
Oh, the improvements are incredible. First, the spectral purity, basically how clean the X-ray wavelength is, improves by more than 100 times. Imagine listening to a pure musical note versus static-filled noise. Second, something called temporal coherence improves by over 1,000 times. That means the X-ray waves stay in perfect sync for much, much longer.
And that matters because...
It matters for basically everything. When you're trying to figure out the exact structure of a protein, or watch atoms move during a chemical reaction, or do quantum physics experiments, you need your X-rays to be pure and consistent. With the old XFELs, every pulse was different. It's like trying to take a photo with a camera that has random exposure settings. This new cavity-based laser is consistent, stable, and way more precise.
So what can we do with this that we couldn't do before?
So many things. Scientists can now do quantum optics experiments with X-rays, which was basically impossible before. They can measure atomic structures with insane precision. Imagine measuring the width of a hair from across a football field. And the stability means you can actually compare measurements over time, which is huge for studying dynamic processes.
Could this help with medical stuff? Better X-ray imaging at hospitals?
Eventually, maybe, though we're not there yet. These are still big research facilities. But the improved coherence could lead to new imaging techniques that capture molecular-level details in biological samples. We might be able to see disease processes at their most fundamental level, but that's more of a long-term possibility.
How long did it take to build up to this? This seems like a massive breakthrough.
Decades of work. X-rays were discovered in 1895. And for over a century, they've been incredibly difficult to control. We could generate them, use them, but truly taming them, making them behave like well-controlled laser light, has been this huge challenge. This is honestly one of those fundamental physics breakthroughs that opens up entirely new possibilities.
I love those moments in science where something that seemed impossible suddenly becomes real. What happens next?
Well, researchers will work on making these systems more powerful, more stable, and hopefully more compact. Right now, we're talking about big national lab facilities. But imagine if this technology could eventually shrink down to something more universities and companies could access. And people will start doing experiments that literally weren't possible before. That's when the really surprising discoveries happen.
The discoveries we can't even imagine yet. That's the exciting part.
Exactly. That's what I love about fundamental physics breakthroughs. Someone just figured out how to make X-rays sing in harmony, and we don't even know all the songs they'll sing yet.
That's a great way to put it. Okay, I'm officially excited about X-ray mirrors now.
Mission accomplished. Thanks for geeking out about laser physics with me, Mike.
Always a pleasure, Sarah.
Thanks for listening to SciSense. Share it with a friend. See you next time.